Howdy, everybody. Hope you're doing well, whenever you are. We are here for the last part 5 of our Z3 Rust tutorial. I've had a lot of fun doing this. I feel like I've learned a lot. This last part's going to be more application related. Like, we're just going to try and solve 3 problems with what we already know. I do have some additional things that I've continued to learn about, and so I'll show you some new ways to do some things that we've done before. It's not that the way that we've done it before is necessarily wrong or bad, but there's additional ways that are more SAT oriented, and I'll show you those. Again, there's multiple ways I think to solve these problems with Z3, but there are ways that you can find optimizations if you need to, so I'll show you. Other than that, let's just get started, I guess. How did your homework go? Did you do your homework? Should we go look at the solutions? If you remember, this one was a map coloring one. The idea is you're going to be given a graph, and you're trying to apply colors to each of the areas such that no two areas or no two adjacent areas have the same map. So you can see here's the example, right? I think we went over this before. Like if we color this one green and then this one red, and then I don't know, this one purple, we now have some constraints on some of these, right? Like this one is connected to this one and this one's connected to this one. So you might say, okay, well, I'll label this one. I can label this one green, but now the only thing that can go here is purple, right? Because if you put any other color here, it'd be connected to the two. So this does still technically work, but you may start running into problems as you come through here, right? So if we put say we put purple right here, purple right here, purple right here, right? The idea is you want different colors all over the place. The question is how do you solve that and do that? And part of the problem with these ones is question is what are the minimal number that you can do, right? So maybe you try it with just 2 colors and it doesn't work, and then can you try it with 3, and so on and so forth. I think for this one I had mentioned that you could kind of do it interactively, like I had done with Ratatouille and the Shidoku. Obviously, though, that's a little bit more involved. And so the other thing the other approach I gave you was to do it in a more programmatic way, where the solver is used to check to see if you've met the constraints, and then you can do a DFS or something like that, which is what we'll do. So I'll show you that. And the reason why I think that way is kind of cool and worth thinking about is, imagine you're building a video game or some kind of board game or something like that online. You may have certain constraints and certain rules of the game, and you want to make sure that all of that state is maintained. You may want to ask, is this a valid move, or is this something valid that you can do? And the Z3 solver can help with that. So let's look at my solution. I created a little graph struct that says, how many nodes are there, and then here's the edges to the nodes. And then here's my implementation of the Peterson graph. So you have that outer cycle, the spokes, and then the inner star, right? And so this is just me creating the map. But the meat of it is how do we do the constraint, right? And so I'll show you how that looks. Well, we create a constant, an integer constant, or an integer variable for each node in the graph. And so you can imagine each of these values right here have their own value. And the reason why we do that is then we can track them, right? And then we need to initialize some constraints, right? So the main constraint is we have to be between the colors 1 to 3. I'm just using numbers here. You could use colors, strings if you wanted, but we're saying you need to choose between 1 and 3. And then we assert that the edges are not the same, right? So I notice the not here. That can get missed in here, but we say for each edge, the adjacent region should not equal the other region, right? So we're adding that constraint where we're saying, apologies for the coughing and stuff. If this one is red, we're saying that, you know, this one, and this one cannot be red. So those are the constraints, right? So you can see the rules are actually fairly simple, right? We have some variables, we have some couple for loops to like make constraints on what the values are allowed to be. And then we can just do the coloring solver, right? So this is like the DFS part of it, right? So we're going to create a solver. We're going to do the DFS on the map. You can see here where we start, we print out what we're doing. We have our regions. We have our, this is like our progress, right? We know we need to color every region, and we track which colors we've tried in those regions with this kind of a tempt thing. But then we just loop through it, right? If we've ever colored all the regions, we know we're done, and we can print the solution. Otherwise, we're just going to try each of the solutions, right, for our current position in the stack. This is a normal DFS, right? Excuse me, this is a very normal DFS. We're just tracking the values we've used. And again, if we ever find the values, we've ever used them all, we know we're done. Otherwise, we're going to try all the colors for our current state. And we're going to add a checkpoint here, right? We add a checkpoint. We ask the solver, does this work? If it does, if it's a valid move, then we add it to the list of like valid moves. Otherwise, we pop and keep going, right? And we iterate, iterate, iterate. And so this is the part where you're saying we're going to try each of the colors, just to be clear. And it's going to say, so if we try and put a red right here, it'll be like, that doesn't match. That's not valid. Again, think about this in like maybe a chessboard or something like that. You have an online chessboard and someone says, oh, I want to move my knight here. You can determine if that's possible. And it's not just like, for example, you can add constraints that like you can never make a move that would put your king in check. And so you might say, oh, the knight can move in these like, you know, L shapes anywhere on the board, but they have to stay on the board. But you can also have that king constraint. So then now if a knight moves, the solver can say, oh, no, that's bad or that's good, right? Anyway, if we didn't find a valid color, we backtrack. So this is our, we got to pop our thing off the stack and go back up a level. That's to say, like, if we've tried all the colors and none of them were good. So like that, the idea here would be there. Let's say we have red, blue, and green right here. There's now nothing we can put here, right? So we know that this isn't a valid way, and so we have to backtrack. And so that might be, we say, okay, now let's remove the green and let's try another color here. And we'll say, okay, now we'll try red in that position, right? That's what the backtracking is doing. But that's it, right? It's a basic DFS where we're going to try everything. And we just use the solver to kind of tell us, have we found a solution yet, right? Let's look at it. There you go. It said it found a solution. So, you know, it said, here's the colors that you can use to do the solution. And this is a small node, so a small thing, it's a toy thing. But again, you could imagine a much larger grid or a more complex game with substantial rules. And you can use the solver to kind of assert and make checks that, yes, this is okay, or no, this is not, right? And go through that list. So hopefully that was helpful. I thought that was a kind of cool thing. I always have ideas in my head of like games that I want to make or puzzles that I want to do, things like that. And the idea of being able to use Z3 to do that, I think is a very powerful thing, a very, very cool tool. Okay, the rest of this video is just going to be going through going through 3 problems, okay? Each of the problems, I actually have like a template for you. So for example, in the restaurant one, I have a template for you right here that you can use. And the reason is I don't want you to spend a bunch of time worrying about, you know, how do I parse the input and stuff like that. Just want you to kind of focus on the Z3 aspect of it. So feel free to use this template. The idea is each of the problems have some JSON input that you can give it, either by standard in or passing it as an argument to the program. And then you know, this will do the job of like building these structures for you that you can then use to solve your Z3 stuff. So that's just what we're going to do for the rest of this. And the first one we're going to do is called the Great Family Dinner Debate. So does anyone ever have this problem besides me, where you decide you want to go out to dinner as a family, but you can't ever decide what you want to do, where you want to go? There's some people that just don't care, and so they get no input. There's some people that, you know, have very specific dietary needs, and so you have to pick restaurants there. There's some people that love some places, other people hate other places. Some people that, you know, are meh on some places and, you know, hate others and things like that. And it can be really hard to choose. Well, we can use Z3 to help us figure it out, right? So I want you to think about this for a second. How would that work, right? In this challenge, we want to like use Z3 to find the spot that's going to kind of like maximize happiness, right? Obviously, we need to respect dietary needs. So if there's someone in one of the inputs that's like a vegan, we need to find a vegan place. And again, this is just a toy example, but you could imagine this working more generally for other dietary issues. We also, I wanted to add a stay on budget, right? Different people have different budgets that they can work with. And so we may cap it and say, oh, maximum dinner cost per person is $20 or something like that, right? But then also we want to maximize the happiness, right? So here's our 3 constraints that we want to think about: respect dietary needs, stay on budget, and maximize happiness. Okay. So that's the idea. Is can we write a program that when your family can't decide what to do, you can do the analytical thing, get everyone's preferences and any budgetary constraints and do that. So I'll give you an example of just one right here, right? Imagine in this case, there's no vegans, but there's like 5 different restaurants and all at different price points. And we have like a budget, right? So the question is, you know, given these 4 people, what is the most likely restaurant to pick, right? And so they've each given a rating to each of the restaurants. And then we want to be able to like find the one that fits the constraints of the budget and anything and any, you know, dietary constraints. And then with whatever's left, we maximize that happiness. Okay. So here's another one where there's like multiple vegan restaurants and you do have a couple vegans. So you like have to like say, okay, well, I know I can't do this Burger Shack one in this case because there's nothing for Alice and Bob to eat. But given the other 3 are there any that, meet the constraints of the cost, and then which of these have the highest likelihood of providing the most happiness among all the people. This is a little bit like ranked choice voting, if you've ever heard of that before. Anyway, that's the idea. So we need to think a little bit about like what our variables will be. Like, remember, the overall goal is to write the one, dietary constraints, and 2, cost, and then 3 is we want to maximize happiness, right? These are the 3 goals. Obviously, the dietary is really easy, right? We can do something along the lines of like, if not vegan and vegan in party can't choose, right? That's a pretty easy one for like the dietary solution. The cost one's also relatively easy too, right? Is like you can say like the cost per plate times the number of people has to be less than the budget. Right, so that one itself is pretty easy. Maximizing happiness is also fairly easy too, right? Like, we haven't done, I'll show you another way to do this, but like we kind of want to say like of the restaurants we want to assert or we want to maximize the sum of the happiness for the restaurant, right? So those are kind of like the 3 high level things that we need to do. When we think about like, these are our constraints, right? Now we want to think about like our variables. I think the biggest variable is like we probably have a list of restaurants, right? R1, R2, so on and so forth. We'll have a list of restaurants. And we'll want to associate those with something. This is an interesting problem that's actually been talked about. It's called the pick one. So set pick one, or pick n in general. Maybe I have to do cool that pick one. Hinting at exactly one, right? We want to pick exactly one of these things. So there's kind of a way to do this where you say, I have to pick one of these, but not not more than one. And if you read about there's kind of a lot of ways to do this and to solve this problem. One of the ways to do it in Z3 is to use what are called pseudo booleans that are associated with values, right? And so we assign each restaurant, it's called PB, and we assign each restaurant a pseudo boolean value. So these are all bools, right? And they're either true or false, but we also assign them a value. In our case, they're all going to be 1, right? And then we can tell the system that we want to do a pseudo boolean equal to 1 for these values. And that has the effect of saying I can only pick 1. The cool thing about this is you could say, let's pick the top 3, and then we can have an argument over the top 3, right? So maybe there's a large list of restaurants. People are throwing out names. Maybe you just like whittle it down to a few and then make a debate. You could do that as well in this program, right? We could say PB equal 3 for like our values, right? We could say, oh, I want to do 3 of them. And so that's what we're actually going to do to solve this problem, right? Is we're going to say we're going to create these pseudo booleans, is what they're called, and they're going to be for each restaurant. And then we're going to say each of those, I want them to be equal. I want you to solve it such that there is only one that is like turned on. And this has the effect of, normally what you'd have to do is you'd have to do a bunch of like if then else's. Like if this is chosen, do this. If this is chosen, do that. We'll still do that for some of this stuff. But this pseudo Boolean is kind of a workaround because it allows you to use like the Boolean satisfiability logic that says, I only want you to pick one of these, which means you OR them together, but then you need to AND them for one. You OR one and not picking one of them, I think is the way it goes. Let's look at the code. I think it'll make more sense when we get there. So here's the solution. Yeah, one hot encoding, I think, is another way. Boolean variables for each value, right? So this is the is chosen, right? So each restaurant is going to be given a Boolean for is it chosen? And then we're going to create our constraint, and this is where we do the thing, right? So each Boolean is going to be assigned an integer value of 1, because we only want to go 1. Again, there's a lot of complexity you could do with these like pseudo Booleans, where we could say like, oh, each of them have different weights, and we want to like maximize how many of them we can use. You can use this as well, right? We've done programs like that before where you could do this. I waited to do this until the end because I think it's a little bit more complicated. It's more SAT-like and less just solving-like. But anyway, hopefully this makes sense. So what we do is we say, I want to assert that we PB equal constraints to 1. And so these 3 lines have the effect of saying, given a list of restaurants, you're only allowed to pick one. And then we can do the rest of the constraints after that, right? So we can assert the cost. Have we used implies before? I don't think we have. Implies is like if then else. So we've used ITE before, right? So you have like some bool and you say ITE, and then you have the true and the false, right? You have the 2 clauses that say it. You can also do a bool dot implies, and it just give it the truth statement. So this is like if then, and this is if then else. That's the way to think about those. Sorry, my chicken scratch. But that's kind of the way to think about those, is like if then versus if then else. So what we're saying is like if we choose this given restaurant, it implies that the total cost should be less than the budget we're given, or less than or equal, right? So this is our like if constraint, where we're telling it, if you choose this one, it has to be less than. And so we could do if then else. In the past, we've done if then else where we set it to 0 or whatever, right? We could potentially do something like that. But this implies, I think, makes it a little bit cleaner, where we say assert that if this restaurant is chosen, we need to make sure that the total cost is less than the budget, right? Then for each of the restaurants, we can sum up their happiness and add that restaurant happiness to the chosen value, right? We say if it's chosen, its happiness is this, otherwise its happiness is 0. We do have to do this one in if then else, because we want to sum up these happiness values. Notice I'm returning it here in my iterator. I did do iterators this time through. Hopefully it doesn't make the code too confusing. But the idea here is we're going to have now a bunch of happiness things that say if you pick this restaurant, it gives you this much happiness. So now we can sum up all the happinesses. And right here, I think in the past we've used a fold to do this. You can also use the int add to do this as well. So we like collect all the terms and then we say, hey, the total happiness is the addition of all of those terms. This is just like a little helper function that does the effect of folding like we've done before. But then otherwise we just say, okay, maximize our happiness and then check what is the answer. What is the best one? Okay. So we have learned a couple new things here, a few new functions, but hopefully they're not much crazier than what we've talked about before. Again, the idea is still relatively simple, I think, once you've read through it a couple times and understand it, right? We're going to create some Boolean constraints on the restaurants and say you can only pick one. We're going to check to make sure the budget is okay. We're going to use implies for that one. And then we're going to calculate the restaurant happiness if it's chosen. And we're going to sum up all the happinesses. And we want to say, I want you to maximize the happiness based on those constraints. And then we just check it. So let's try and run it. So here's one solution where there's multiple vegans we have to pick from. And you can see like the restaurant we chose is the Green Cafe. Let's see. This happiness choice one is interesting because it's actually based on happiness, right? So there's we had to pick the one that is most liked by everyone, and that happens to be this one in this case. Sorry. So I will say that like some of these are, again, they're relatively like toy problems, but you can see that it's very cool that the Z3 solver can like solve this problem. Now imagine if there's like 50 people that are in like an office complex, an office lunch, and they each have their different constraints. Maybe besides vegan, you also have gluten-free and things like that. And maybe you need to pick like the two best restaurants to maximize the happiness. One of them could be for the vegans and the gluten-frees, and the other one's for all the people who want, you know, hamburgers or whatever. You could make it substantially more complex to solve that problem. But anyway, I thought this was kind of a fun one. Hopefully you've learned a little bit about more about Z3 by trying to solve this one. Oh, I should have said, I don't think I said this at the beginning. Feel free to pause this and try it yourself. And then, you know, obviously I've helped you through this one, but if you know, feel free to pause and, you know, try and solve it yourself. Maybe add your own things. Okay. Again, we've learned a couple of new things, I think, you know, the implies and the int add, and using these pseudo Boolean values up here to make assertions about picking one or picking n. Hopefully those can help you along your path. Okay, what is the next one? It is nonograms. So have you ever like, oops. I'll get it. This one's really big. Let's do a smaller one. I'll try it here. So this is a nonogram. And the way it works is you are given constraints on the rows and columns. And what it means is when you see a 1 and a 1, what it means is you need to mark 1 here, and then you need to have a gap, and then you need to have a 1. However, where the ones start and end can be different, right? So this is a valid solution like this. But another valid solution might be this. This still works because you have a 1 and then a 1. But also this solution works too, right? You have like 1 and 1, right? With this single 1, it means you could put 1 in any of these spots, right? With this 2, it means you need to put two consecutive values somewhere. So right here would be good, right here would be good, right here would be good, right here, good, right? So the idea is you kind of go through trying to solve these with some kind of like uh, I don't know, logic, finding logical conclusions. For example, one logical conclusion you can make is for this 4, for example, um, if I start the 4 here, it will go down here, right? If I start the 4 here, it will go up here. And notice the overlap implies that we have to put 3 here, and then the 4th value is either going to go here or here. And that now helps us kind of solve some things, right? We know this one's here, this one's here, this one's here, right? This 3 now, in order to get 3 here, we have to put the 3rd one here, right? This one has a 2 and a 1, so we know the 2 has to go here. Well, now we know the 3 has to come from either here or here, so we know this can't be 1. We know this can't be 1. We know this can't be 1 because if we put 1 here, we'd have to put a 2 right here, and that won't work, right? So we know this can't be 1, which means that's the 4, and I think we're getting close to a solution here, right? The 2 now has to go here like this, and so now we have a 1. So yeah, there you go. It's solved. If you've never seen it before, this may seem a little complex, but the gist is that the rows and columns, these things, infer, they say, oh, you have to have 4 consecutive, you have to have 3 consecutive, then you have to have a 2 set like a domino, and then at least 1 gap and another one, but like where that goes can differ, right? Well, the question is, could you write a solver to do this, right? Again, I've got an example for you, and so you can try running it to see like if you can reveal the pattern or whatever to find the solution. So I've got like a 3x3 cross and I think a smiley face that, like, given the constraints, you should be able to solve with Z3, right? So this anyway, give this one a try. See if you can't solve it. Feel free to pause it. Otherwise, we'll go over the solution now. This one is interesting to think about because the question is like, how do you tell this? How do you tell the solver about these constraints, right? How do you tell it, oh, I need to have one with a gap and another one? That can be a little bit rough to think about. And so I think you kind of need some time to like go through that, right? So let's just talk about it a little bit. First of all, like, what are the variables? We'll stick with a 3x3 grid for now. Well, you could imagine that each of these grids are a variable, right? So 0, 1, 2, 0, 2. These each are, and each of these grids are a variable, right? So 1, 3, 5, 6, 7, 8. And so these could be kind of Booleans or integer values. However you implement them is fine. But the idea should be like, the question is it on or off, right? The question is, should I turn these on or off? Okay. Well, now we need to start thinking about, how do I decide whether to turn one on or off? Here's the way I'd like to think about it. If we have a 1, 1 here, like, what does that imply about where these values go? What it means is, like, this 1, there needs to be a 1, a gap, and then a 1, right? So from that, we can kind of infer where the start positions are. This is a very toy example. So because it's 1, 1, we know that, oh, this 4 has to be a 1, this has to be a 0, and this has to be, right? Or like on, off, right? But this this pattern could be used in other places, right? Like if we had a 2 here, like what does that infer? There's like a 1, 2, and then an off. Well, because there's no other one, we actually don't have to do that. So what we're saying is for this 2, we need to have these 2 values. Where it starts is kind of interesting for this one because we obviously can't start the 2 at the 7, right? So we want to kind of be able to say like this 1 comma 1, it has to fit in this box. And we'll say this 2, it has to start, maybe is the way to think about it, in one of these boxes. So the 2 has to start in one of these boxes, but it can't start here. And then we can ask, well, where does it extend? Well, if it starts here, then it extends to right here. If it starts here, it extends to right here, right? There'll be some extension of how it goes. But and so that's kind of what I'd like to say we need to think about. And so what we need to do then is we need to take each of these like constraints on the rows and the columns and label the constraints for each of these values. And then given those constraints, we can tell the solver how to do that, right? And so let's just walk through it. I think it'll make sense again as we get to it. The main part of the program is actually not that big, right? We have our grid, and so we create a value for each of our things. And I'm going to use a Boolean, whether it's toggled on or off, right? So for each of the cells in our grid, we're going to create a Boolean variable that's going to say, is it turned on or off? Then we can just loop through all the row constraints and all the column constraints and build up that like row or that column. And then we can say constrain, call this constrain function on those things, right? So given our clues, given our line, which is like, our row or column, here's the constraints that I want you to make. Then I can just say, hey, go try and solve this problem, right? Z3, can you try and solve this? It's where the Z3 gets a little bit complicated. So I'll show you how I solved it. Again, there might be other ways to do this. So like I had said, the way that helped me the most was think about what the valid start positions are and how far they can go, right? Again, we can't start at the end if there's like 2. And then we want to constrain each cell based on whether or not it's within range of one of the start positions. Okay, we want to say like, oh, each cell how do I say this? If the start position is here, and this is a 2, then this value needs to be part of it. Okay. And it can be a little hard to think about why this works. It makes more sense it might make more sense in a larger grid. But if I know this is here, it's like let's imagine this extends further for a couple more. I say, if this is here, this one has to go here. And so like if I have like a 1, I know that this 1 can't start right here. It has to start right here, right? I also can't say that if I'm solving for that 2, I also can't say, oh, well, that 2 solves here and here. That doesn't work, right? So that's what I'm trying to like tell the solver is like, based on the clues and based on the start positions, how can you find good places that fit those? And the cool thing about this is we just do it for each row and column, and then it will figure it out for us, right? It was kind of like the logic I was saying before is like, if this is a 1 and a 1, we know that it like has to fill this one and this one. And so now we know this 2 is either this one or this one, right? It's got to be one. It's one or the other. So we got to pick which one that is. And so we say, if this is the one, then this is the second part of it. Okay, so let's look at that constraint line. We're going to create our start positions for each block, right? So we're going to say, we're going to create an integer variable that says, for each clue, where does it start? And that's what this is, right? Where does each clue start? So again, like this 2, we're saying, where does it start within here? We need to add some constraints for that, right? It has to be greater than or equal to 0, and it has to be less than the cell length, right? The start plus the lane. Again, I can't put a 2 here in this one. I can't start the 2 there in that one, right? So that's what these are doing. And then I need to say there can't be an overlap, right? So I go look at the previous one and say, hey, like with this 1, 1, I say, if I put it here, I can't put it here. And that's essentially what I'm saying, is there needs to be a gap between these. So that's what that thing is doing right here, right? We want to create a gap. And again, this is all stuff that we've done before, right? We have a const where we're creating a new variables for each of the start positions. And then we're asserting some like constraints on where you can place them based on, you know, the rules of the game. Then for each clue, oh, well, I should say, if there are no clues, then we want to assert that each of the cells are empty, right? The assumption is like, if there's no clues, there's no values there. And so we can just say, oh, assert that the cell is equal to false. This AST equals is something we probably haven't used in the past. It's nice to do it here. Oh, it doesn't have very good documentation. The difference between this and like cell.equal is like, this allows you to pass an entire tree of like the abstract syntax tree, right? So maybe you've done a bunch of Boolean logic, and then you need to assert that that Boolean logic finalizes to, in this case, false, right? It makes more sense using it down here, and I'll show you. This is like the most complicated part, and so don't feel bad if you don't understand it. Sometimes I look at it and I'm still like, how does this work? So, but again, what we want to do is like, for each of the clues, we want to constrain each cell such that if it's between that clue's start and its length, it's included in that thing, right? And not in any other one, is maybe the way to say about it. So that's why we AND them and OR them together. These are 2 new things that we haven't used before, bit and bit OR. So we have used ANDs before and things like that. But in this case, right, like in the Rust programming language, you might short circuit if you do an AND. But in this case, ANDing might be okay when you're ORing, right? You still may want to set a cell to true, even though the AND is true, even though the first one is true, you want the next one to be true as well. That's what these bit and bit ORs do. So what do we do? So we're going to iterate through the line, each of the values in the line, right? And we're going to say for each of the starts and the clues, so we're going to zip those together. We have the start position and the clues. We're going to say that the start has to be less than or equal to this cell's position, and it has to be less than the start plus the lane. This is saying it has to be within that. It has to be within one of those things, and we do that for each of the starts and clues. And then we reduce that by ORing them together. Once we've done that, we can then say, hey, this cell needs to be constrained by this logic. What is this saying? It feels very confusing, but I want you to think about like what it's saying about this, like this particular cell right here. What it's saying is right here, it's saying you need to be a part of the one or this one, right? We have 2 of these things. You need to be in here or in here. And if you're not, you need to be like a part, or you need to be a part of none of them, right? Like that's your choice, is you have to be in here or none. And so that's what this has the effect of doing. And I realize this is a little bit confusing. I apologize that, but I think this was, in my mind, this was the best way to think about it. Again, what we're doing is we're going through each of the cells in the thing, and we're creating a variable for it. And we're saying that variable position has to be less than this and less than this, meaning it's like inside that. Sorry, it has to be less than the start and less than the end, right? This is, we're saying like for each of these, we're the one and the ones, I apologize, it makes it a little bit hard, but we're saying like you know, if it starts at 0 and it ends at 3, we're saying like I has to be less than or equal to 0 and 3. We're saying that this cell has to be inside one of these things. And in this case, it's, I guess it would be 0 or 1. And then we OR these together, saying one of those, we have to meet one of those. It has to meet one of those constraints, right? It has to meet one of them. And then we do that for each of the cells. And what we do again, so we say we want to assert equal that this cell is equal to these cell constraints. So we're adding these constraints to this cell. That makes sense. Remember, this is a pointer to the original cell up here that we built. I realize this one's a little bit more complicated. I hope it will show you the power of it, though. That we can do some very crazy logic here. This is like, if you've done Boolean satisfiable before, it will probably make more sense. But again, at a very high level, we're just asking ourselves, we're saying for each cell, you need to be in one of these things, one of these states. And so we say you need to be in one of these, or one of these, or one of these, right? That's what we're doing. I hope that makes sense. But then that's it. It will solve it. So now we can do the here's the smiley face one, and you can see it prints out the solution, which is a smiley face. Here's the code. I printed this one out on purpose so you could see. You can see I'm creating a variable for like each of the sections, right? Or each of the cells. But then here's all of those integer constraints I had, right? So for row 1, there's like 2 values, right? For row 3, there's 2 values. I have those integer variables. And then you can see they're used here in this, like these asserts are hard to grok because they're a giant abstract syntax tree. But you can see what's happening here, right? We're anding together a bunch of these things, and then we're ORing together. Sorry, it's these things. We're anding together these things. Again, what we're saying is this A1 thing needs to be between this section or this section. And so we and the inner values together, and we OR we OR like the first one, and we and the first section, we and the second section, and we OR them together, meaning you have to be in one or the other, or none, right? So we also, that's kind of implied in the work, is like, if you're going to put a value here, you have to be part of this one or this one. But that also works from the column thing, right? So you can see down here we have like column constraints where we say, oh, for each of the columns, we have these like specific constraints that have to be met as well. But again, look, it solves it. It solves an Nonogram. And it actually solves these very complex ones. I won't do this live, but you can see these like giant 25 by 25 ones that are absurdly hard, right? So this one is like, you have a 10, 10 here. And so you know that like some of these values in the middle, like around here, not very well, but like some of the values here and here have to be set. This is not exactly right. It's not even the right column, but you know, it's saying like, oh, these have to be set, these have to be set, something along those lines. These ones can be very hard to solve because you have to like find these things, and this program will actually solve it, right? Which I think is very cool. Okay, that's the nonogram one. Again, I hope you'll understand that like some of this may be very complex, but it's just it's me building the solution around these these values right here, right? Is me saying, oh, I'm worried about each cell, whether I should turn it on and off, and I'm worried about, is that cell in this constraint, or is that cell in one of these constraints, right? And then by merging those two constraints together, it creates this logical like Boolean satisfiability for like all the values. And again, I what it means, I've probably said this a bunch, because there's like two things right here, right? This value right here has rules for this one and for this one, right? So like turning this one on implies things happening here and here, and so adding all those ands and ors together seems a little crazy. But when you've done all of those ands and ors together, the solver can then say, oh, here's what happens if I like flip this one on. It has this cascading effect of the other things that I need to flip on or off. And then the question is, does that solve the problem? And if it doesn't, then it can try other values, right? There you go. There's the nonogram solver. Okay, the last one I want to do today is nanobots. Let's go to the README first and talk about it. This is kind of inspired by part 2 of an Advent to Code challenge from a few years ago that was extremely hard. Unless you had very specific like math knowledge that you could like find some mathy ways to do this, which I don't think I have. This one was very hard to solve. Here's the actual day. The idea is you have a bunch of beacons, and they all have different distances from each other, or they have positions in space right here. So all the beacons have a position in space and how far they can signal, right? So this one has a range of 4, and what it means is it can talk to anything that's 4 Manhattan distances on the XYZ away from the others, okay? And in the first part, it's not too hard. It basically says, hey, find the one with the largest range, and then find how many of the other beacons are within that range. So you can see in this case, it says like that the total is 7. There's 7 within the range of the 0, 0 position, right? So this is in range, in range, in range, in range. This one's not, right? It's too far away. It's 5 positions away. So that one's not too hard because you're picking a single one. Where part 2 becomes more complex, they give you another example. It says you need to place yourself in range of the most of these things. So can you pick a position in space that puts you in range of most of these? And then if there's multiple positions that like put you in the range of most of them, like let's say there's 2 positions that put you in range of 5, you want to pick the one that's closest to the origin. That is 0, 0, 0. And then the way you solve it is given a coordinate, given the XYZ coordinates, you print their sum, right? And that tells you like that's how you want to solve the answer. If you think about this for a minute, that is extremely complex, right? I'm only going to do this in 2D space, but imagine you have beacons all over the place, and they all have ranges, right? They all have like these radiuses around them. I'm not drawing this very well. right? You want to pick something that like some position that puts you in range of most of them. And it's probably like somewhere in here, right? So you can say, oh, I want to kind of like search in this space for something that puts me in range of all 4 of them. Admittedly, with 4, it's relatively small, right? It's kind of like a toy solution where you say like, oh, I can just say like, okay, well, find the overlaps between these 2, find the overlaps between these 3, you know, and then you kind of like keep doing this overlapping thing until you solve it. But when there's a lot, it can be very hard to solve, right? There, and in fact, in the puzzle, there's like, I don't know, 1,000 of these. So how do you ever try all of the 1,000 different possibilities? Is like, it basically, the number of choices you can make is infinite. It feels like, right? That's technically not the case. Again, there's like kind of a mathy way to go about solving this. But for me, it felt impossibly infinite, right? There's just too many solutions. And this is where Z3 can help you like solve a complex problem like this, right? So think about what we want to solve here for this Z3 thing. Again, I gave you an example of the or a template that you can use. So go ahead and try and solve it yourself with Z3. Feel free to pause and solve it yourself, but I'll walk through my solution with Z3. I'm not going to do the actual mathy solution, but let's do the Z3 solution to it. Okay. What are our variables, right? Well, I actually think there's only like, I mean, there are some, we'll look at the code, but at a high level, we're really only interested in the target, right? So it will have some X, Y, and Z values. And we're only really interested in these things, right? And then just the question is like, what is the distance between between this XYZ coordinate and each of the bots, right? So maybe B0 is like 5, 7, and 9, and B1 is 1, 1, 1, and I don't know, 2 is -3, 1, 4, right? So the question is like, what is the distance between this target and this one, and then this target and this one, and then this target and this one? And then we can tell the solver, given all these constraints, can you find some variable? Can you maximize the number of targets? Hit is maybe the, it's not hit, right? It's maximize the target in range, right? That's kind of what we want to tell it, right? Is we don't know what these X and Y's are, but we know that if you can calculate the distance between these values with these values doing like a Manhattan thing, right? So this one right here is maybe we'll do this one down here, just an example. It's going to be the absolute value of X plus -3 plus the absolute value of Y plus 1 plus the absolute value of Z plus, right? That will give us like the Manhattan distance. So we don't know what, again, we don't know what this is, but we can do that same thing here and here for each of the bots. And now we have like a list of equations that will tell us where these distances are in relation to the bots. Like, what is the relationships between this target and all of these bots? And then we can just simply tell it, hey, can you maximize the targets in range? So that's what we're going to do in code, is we're going to basically do this distance calculation for the given target for each of the bots. And then we're going to tell it, can you solve that for us? Okay, if you look, this code is not actually that complex. There's not a lot to it. And I wanted to finish with this one because I think this shows you like the very cool power of Z3. We've solved all kinds of things. We've used, we've learned about implies, PB equals, if then else, joining them together with adds or folds, things like that, right? We're still going to use some of this stuff, but we can, it's not a lot of code, right? Basically, we say we're going to create our target coordinates. Again, these are our variables, our X, Y, and Z. And then for each of the bots, we're going to calculate its distance. And again, this is like the distance. Oh, I did double bars back there. Sorry. The distance is just the distance of the X's, the Y's, and the Z's, right? The difference. Did I do plus as well? Can I say that I have a cold? Should we do this one more time? Because I did it so terribly that time. I apologize. I should probably do it again. It is. So this one is X minus -3 plus Y minus 1 plus E. There you go. That's what we're looking for. And so that's all this thing is doing. The one thing the one problem you run into is that we don't actually know the values of X, Y, and Z, right? They're variables, right? So we need to build this distance formula for each of the X, Y's, and Z's. And so that's what this helper function is, right? You give me the target coordinate and the coordinate of the bot in that same axes, and then I'll create a variable for it, right? Where we say like, give me the absolute, and this is doing is like the absolute value of the subtraction of those things. So we say the diff is A minus B and the negative diff is B minus A, right? We swap them. And then we just say if A is greater than or equal to the B value, then we do the diff. Otherwise, we do the negative diff. This is just an easy way of saying we want to do the absolute value. I couldn't find a quote unquote absolute value in the library, but this is the way of doing it, right? Like it has the effect of like, let's say X is -1, and we minus -3, right? We want, that's going to be -1 plus 3, which is 2, right? If we did it the other way, though, it'd be -3 minus -1, which would be -3 plus 1, which is -2, right? Which one of these is the absolute value? It's this one right here, right? So we want to pick this one as the absolute value. That's what this distance formula is. You have to do it programmatically or in Z3 parlance, again, because we actually don't know what this X value is, right? So we can't like solve it, but we can tell Z3 how to solve it, and that's what this is doing, right? So basically we just say the distance of the X's plus the Y's plus the Z's, and we just say you're in range if that solved distance is less than or equal to the bot's range, right? So we say, you can check it off if that is less than the bot's range. So let's say it's 4, 2, and 1. So that we'll say this one works, but then this one doesn't work. Like that's what you're doing. You're saying if you put your XY here in these positions, here's how you can tell if you're in range of these things. That's what that's doing right here, right? We say, are we in range? And then we just do a soft constraint, right? We don't say you have to be, you have to pick this bot. We just say, if you are in range of this bot, we'll give you 1 point. That's what this is doing. If you're in range of this bot, we'll give you a point. Notice we use none here. I think we talked about this last time. This symbol is like a grouping, and it asserts groupings together, right? In this case, there are no groupings. Each bot is its own grouping. So you'd never pick between two bots. You would just determine if a bot is within range, and if it is, you include it. If it's not, you don't, right? We're not picking between multiple bots, so our assert soft has no groupings, but we still assert soft that say, hey, if we're in range, you get 1 point for this one. And remember, it's trying to maximize the number of points that it gets, right? So there's our initial constraint, our initial set of constraints where we say, given these variables, here's how you calculate the distance for each bot. Here's how you can tell if you're within range of the bot. And then you get a point if you put this bot in range. Now there's a secondary thing, right? We want to minimize this value right here. So we're technically doing two things, right? We're telling it to maximize this and minimize this. I think in my first code, I actually called maximize this value and minimize that value. We've never actually done that before, but it's totally possible to do. You can say, I want to maximize this value and minimize this value. Or you can say, I need to minimize these two values together, and then it will try and minimize those two values in conjunction. Okay. But we're kind of giving it two things, right? We're saying, try and maximize this, right? Get the most of these you can. But given those constraints, minimize its distance between the origin, right? Then we just tell it to solve. Let's try it. So here's the sample. You can see it finds it almost immediately. It says, oh, the solution is 36. The best coordinate is 1212. It found this one absurdly fast. I'm going to go to my Scratch and run it here, just so you can see it actually solves the actual puzzle, the part 1 puzzle. This is my like Scratch code, a Scratch library when I'm testing things. You can see it's taking substantially longer. Why is that? Well, there's 1,000 nanobots, right? So we've created 1,000 of these different like distance variables, and we've told it, hey, you get a point for each bot that's within range, and you lose a point, obviously, if you don't put it in range. But I want you to find the value that's the one with the largest number of bots closest to the origin. And you can see it solved it. It took several seconds, right? But it actually solved this problem, right? Look at all these values, and they're very large numbers, right? They're absurdly large, meaning there's just so many things to choose from. Again, you could probably do some analytical mathematical things to solve this problem. We can just throw it into Z3 though, and solve it with this, okay? Maybe you don't want to solve all of your puzzles with Z3, I understand, but it can help you to like get to a solution or to check a solution, right? And you're like, wow, why am I off by, why can't I solve this problem? Go solve it with Z3. And then you can and then you can say, oh, I was off by 1. Is there a bug? Where's the bug in my code? What am I missing? Or what am I not doing right? Again, look at the simplicity of this code, right? We're not doing a lot. Again, there are definitely ways to optimize this. There's definitely mathy ways to find a suitable solution. But for a very little amount of code, we can solve a very complex problem that would be very difficult to solve. And that's the power of Z3. Okay, let's wrap this thing up. I hope you've had a lot of fun learning about Z3. For me, it's been really helpful. That's why I like doing these types of videos, because I feel like it helps me learn more. And Z3 is definitely something that I haven't used a lot of. Now I feel like I would put myself in like the intermediate category, where I feel like if you gave me a puzzle, I could probably solve it with Z3. I definitely have to look at the API for some things or look back at code. I couldn't just like start typing it out blindly, but I definitely think I could get there. And so I think that's been good. What will I say? If there's to close this off, the key to remember is ask yourself those 3 questions, right? What are my variables? What are my constraints? and what am I solving for? Like if you can write those out, you notice I've done this with like every single problem. I kind of draw it out to think about it, right? I need to draw it out and think about these. We've done it multiple times, right? We kind of draw it out, we think about it. I apologize for my chicken scratch, but drawing it out and thinking about it helps you get to the say where you can say, okay, I think I know now how I can put it in the solver. So don't feel bad about thinking about those 3 steps, right? Is what are my variables? What are my constraints? What am I solving for? And if you can find those 3 things, you can put them into the solver and solve the problem. The other thing I'll say is, and I've said this multiple times, look at the power of Z3. Isn't it cool that we have a tool like this that we would just not have had, 20, 30 years ago or whatever? That we can take very complex problems, multiple variables. We can do pick ends, pick ones, like the best restaurant. We can do constraints like the button pushing one, or we want to minimize pushes, but get to a specific target. You can solve examples like my family keeps fighting over restaurants. How do I pick the best restaurant, right? Can use it to, maintain game rules in your game engine, right? To ensure that people aren't, breaking bounds or doing things that are illegal moves and stuff like that. I think that's really cool to think about how Z3 can be used to do that too. So the uses that it has, obviously we're a puzzle solving website or puzzle solving channel. So I love to solve puzzles. There's definitely use cases for it there. But I think after doing this, it's expanded my mind of like, how can I use this at work? How can I use this at home? How can I use this for, my toy programs that I've been working on? I think there's a lot of cool ways to use it. And so I just say, keep it in your back pocket as another item of ways that you can solve problems. And then when you're asked to solve a problem, don't hesitate to pull it out to help solve a problem. I think it's a really cool way to do it. And it's a very, it can be very analytical, mathematical formula, but it can also just be, here's my chicken scratch. We didn't do any math. We did very little talking about Boolean satisfiability, which is a very cool topic, right? It's talked a lot about in computer science is like, how do you solve these satisfiability problems? There's also a lot of talk about like, how do you can you turn a problem into a satisfiability problem? And so there's lots of work that goes into doing those things. It's led to a powerful thing like Z3, but we don't have to know that stuff, right? We can still just use the tool that it is. Maybe you're interested in it, and like I am, and then you can go read more about that stuff and how to do it. But you don't have to know that stuff, right, to be able to solve these problems. And I hope that's what you've gotten out of this video. It's a very cool analytical tool, but you don't have to be like the super math nerd with, the pocket protector and the glasses. Did I do that type thing? To be able to use Z3 to solve some really cool problems. So there you go. Hopefully you've had fun. Hopefully you've enjoyed this. I've really enjoyed it. And we'll see you in the next video. Thanks, everybody. Bye.